All right, this is my critical assignment preparation 2 for the fated lactate. My name is Roger Richard, and this is for KIN516. So here's the diagram that I drew up. Down here you see the muscle here where we've got glucose turning into lactate, lactate going into the bloodstream, and then from the bloodstream it goes into the liver where that lactate through glycogenesis becomes glucose, which then is sent back through the bloodstream to the muscle. So to break it down a little bit, what are the key steps in the pathways illustrated in the diagram? Like I mentioned, glucose is broken down through glycolysis into pyruvate. This reaction costs 2 ATP, but then produces 4 ATP. So there's a net yield there of 2 ATP. The key here is oxygen's presence. So if there's oxygen, if oxygen isn't present, the pyruvate cannot be converted into acetyl-CoA. Without acetyl-CoA, the Krebs cycle and electron transport chain are not active and lead to a buildup of hydrogen atoms. Pyruvate then bonds with NADH and lactate dehydrogenase to form lactate. The increase in the free NADA molecules accepting hydrogen drops the pH level of the blood, which could eventually cause the muscle to stop contracting. Some more of the key steps, and now we're talking about that lactate now being transported through the bloodstream, and because the body enters the Cori cycle to help flush the lactate. That blood is then moved to the liver, where the second phase of Cori cycle takes place in the liver. The lactate will be reconverted back to glucose for use in the muscles. Again, lactate dehydrogenase helps in this process, kind of like it did before, and now that lactate is converted into pyruvate. Once it's converted into pyruvate, it goes through glucogenesis, which allows the 2 molecules of pyruvate to convert to 1 molecule of glucose. However, this process actually requires 6 ATP and actually produces none, so it's pretty expensive to do. It's an expensive energy process, but is now ready to get back into the bloodstream and return to the muscles. This first question here second question is, how are these pathways affected by exercise intensity and training adaptations? Some of the effects, these pathways kind of continuously exist, just at different degrees at different times, kind of depending on exercise intensity. They even actually happen at rest. With high intensity exercise and a low oxygen presence, the Cori cycle is very active. Like anaerobic exercise. With lower intensity and even moderate intensity, lactate is still being produced and shuttled through the blood through the Cori cycle, but just at a much lower rate. It's during this time that the liver actually kind of restores and replenishes its glycogen stores. Some of the adaptations, or some of the type of training adaptations you can get is if you were to use like an increased steady rate of exercise. So every time you exercise, you increase the rate of exercise just a little bit more. The oxygen intake would match the level of exercise up to the lactate threshold. But then the following time, if that exercise increases again, then that threshold is now a little bit higher. And so as exercise increases, so does the threshold. There's also maximum capacity for oxygen. Each breath will allow you to take in more oxygen. So the more activity you do, the more oxygen you take in. An increased oxygen uptake allows for less Cori cycle, because Cori cycle happens in the lack of oxygen, which helps you kind of produce more oxygen for oxidation of the substrate. So, breaking down glucose to provide more energy for more activity. How do lactate and lactic acid differ? They kind of get used interchangeably, actually, but lactic acid can give a proton, lactate can't. Lactate is actually produced from the deprotonation of lactic acid. So it's the base form of lactic acid. Lactic acid has an intramolecular hydrogen bond. Lactate doesn't. Lactate is the conjugate base of lactic acid. Lactic acid can pass through lipid membranes. So they differ in a few ways. They're often used interchangeably when talking about muscles and liver and exercise and activity. Can lactate be used metabolically? If so, when or under what conditions? By itself, as lactate, no. However, because it can be converted into pyruvate, it can be used metabolically. As mentioned before, if it's turned into pyruvate, then it can eventually become glucose, and that glucose can be used for energy purposes. Some of the consequences and key factors, what are the consequences of lactate accumulation on our ability to sustain exercise? The increase in lactate accumulation also means an increase in the acidity and a lower pH. Lower pH can lead to muscle contractile failure, so the muscles stop contracting. The body kind of produces lactate or lactic acid as a safety precaution when there's an extended anaerobic state. So if we're doing an activity and there's a lack of oxygen for an extended period of time, that lactate or lactic acid builds up to prevent us from injuring ourselves, to kind of stop us from contracting our muscles. Much like the handbrake on a car, you're just getting out of control. You hit the regular foot brakes, and then as a last resort, you pull that handbrake to stop all movement. What are the other key factors at work at the cellular level that could cause exercise cessation? Lactate shuttling is expensive. Like I mentioned before, it uses 6 ATP plus the 2 original ATP that created the lactate from the beginning, and the net production there. So it produces 2, but it uses 6, so we're losing 4 ATP every time we do that. Eventually, the loss of 4 ATP per trip through the Cori cycle will add up, and the muscle cessation is imminent. It's bound to happen. So the idea, the more oxygen we can get in, the more oxidation we can do, is obviously more efficient and better to use in terms of producing ATP than lactate. That's it. Thank you.